All right, everybody. Hello. So today I'm going to talk about some additional concepts that we haven't discussed, but they're very relevant to public health. So we discussed risk already. Risk is akin to to a new case, right? To incidents, right? So risk and incidents are synonymous. Relative risk is a measure of risk among the exposed in comparison to those who are not exposed. You can do it other ways if you want to, but generally we look at whether the risk among those who are exposed is higher than the risk among those who are not exposed. So relative risk is one way to make that comparison. However, it's not the only way. Today we're going to talk about attributable risk. So this assesses the proportion, and again, I say risk and incidence are the same, proportion of the incidence among those who are exposed to a risk that can be actually attributed to the specific exposure. So this figure shows us the risk among those who are exposed. So this bar here on the left is the level of risk. And these are some arbitrary markings, numbers here. Scale is arbitrary. And this risk is composed of specific risk due to that specific exposure and background risk, the risk that anybody would have whether or not they're exposed to the specific risk factor. So we have the risk among those who are not exposed. So they're going to have some risk. So this background risk is the same as the risk to anybody who's not exposed to the risk factor. So we could be talking about lung cancer and we're looking at cigarette smoking. Yes, cigarette smoking would be a specific cause, but there are other factors that cause lung cancer, right? Including smog and other type of pollutants. So the question is, what proportion of the risk is attributable to the specific risk factor? So if we look at the first figure here on the left, we'll see that the incidence, again, risk and incidence are synonymous among the exposed as the sum of the background risk and the specific risk. To calculate attributable risk, we simply subtract the risk among the non-exposed, right, from the incidence among those exposed. So basically, we're just taking out this amount and we're left with the specific risk. That's what we call the attributable risk. We can express it as a proportion as well. We can take the attributable risk, again, that's the incidence in the exposed minus the incidence in those who are not exposed, and we can divide it by the incidence in those who are exposed. So that'll give us the proportion of the incidence in the exposed that's attributable to the specific exposure of interest. So that's when we're just looking at attributable risk, and we're really focusing on those people who are exposed to the risk factor. We can also look at the population attributable risk. That's the risk to everyone, not just to those individuals who are exposed. So to calculate this, we have to use some weights. So weights, we're multiplying by some proportion, the proportion of people who engage in the risk factor, risk behavior. So the population attributable risk is the incidence in the total population minus the incidence in those who are not exposed. That's the same background risk as what we were dealing with before. And we can express that as a proportion too. The proportion of incidence in the entire population, again, it's the population attributable risk, or the incidence in the total population minus the incidence in the non-exposed group, divided by the incidence in the total population. So let's do some examples here and work these out. Here's a textbook example. And again, I'm using the Gordis textbook, right? Epidemiology textbook. So here we have the example from the textbook. We have healthy smokers and healthy non-smokers, right? So these are healthy individuals, right, at the beginning of the study. And then we have some of those, but they are engaging in this risk factor, risk behavior, smoking. And we're talking about combustible cigarettes here, right? Not vaping. Some develop coronary heart disease and others do not. So this is our cross-tabulation table. And if we just wanted to calculate the incidence, that wouldn't be that hard to do, right? Because the incidence is just the number of new cases again, said we started with healthy individuals. So if somebody develops CHE, they're a new case. So we could just calculate the incidence among healthy smokers. And that would be 65 divided by 2,000. So this is our risk among the exposed. So in calculating the attributable risk, if you recall, the first element here is the risk among those exposed. That includes both the risk due to the exposure and then the risk that's the background risk, right? And here's that background risk. That's a risk among those who are not exposed. Those are healthy non-smokers. We have 20 divided by 4,000. So we subtract the risk among those who are not exposed from the risk among those who are exposed, and we multiply it by 1,000 because my goal here is to provide the incidence of CHD in smokers per 1,000 population. So we get 27.5 per 1,000 individuals. Okay. That's a very simple type calculation, but like everything in epidemiology, you always have to be very cautious to make sure you follow every step. Log everything along the way. You're building towards this beautiful final product here. The proportion of the total incidence in CHD in smokers that is attributable to smoking, well, that would be the attributable risk, right? Divided by the total, so divided by the total risk among those who are exposed. Again, we're doing the proportion of exposure among the exposed that's attributable to the risk factor. So we're just taking this value and dividing it by the total, right? And I don't have to multiply by 1,000 here because it's kind of irrelevant. I'm just trying to get a proportion. And if you did, you'd have to do everything by 1,000. It seems kind of a waste to me, but it's, you know, it's not necessary here. We don't have to multiply the numerator and the denominator by 1,000. We can just leave it out. It would cross out anyway. So we get, well, this is the same, essentially the same value we had before, right? Same values we had before. And in our denominator, so we get 0.846 or 85%. So how do we interpret this result? So we can reduce the number of CHD cases among current smokers by 27.5 per 1,000 per 1,000 individuals by having them quit smoking. That'd be awesome, huh? Or we can reduce the risk of CHD among smokers by 85% by having them quit. So that's interesting, right? So that just gives us some guidelines for practice. Let's look at population attributable risk. So here's what we know. We know, and these are just made up values, of course. So this for our purposes here, incidence of lung cancer in smokers is 9 per 1,000. 9 per 1,000 population would be 9 people out of every 1,000. The incidence of lung cancer in non-smokers is 1 per 1,000. So it's like 9 times less, basically. But because we're doing population attributable risk, we have to understand what smoking prevalence is in the population. And we have to apply this weight, we're going to call this a weight, to these values here. Okay. So smoking prevalence as a percentage of the total, imagine we lived in a world where the smoking prevalence was 45%. That would be horrible. But it's for our example now. So the smoking prevalence is 45%. That actually translates to a probability of being a smoker equal to 0.45. Probability of being a non-smoker, so that's the incidence among, the population of non-smokers, I should say, is 1 minus the probability of smoking. This is the rule of complementary events in probability theory. So we get 1 minus 0.45, and we get that equal to 0.55. So these are the two values we need to proceed. To derive the incidence of lung cancer in the population, so now we're doing the entire population, not just smokers, we weight, this is called weighting, we weight the incidence by the population prevalence. So the population incidence would then be 9, because we have 9 per 1,000, right? For smokers, but 45% of individuals are smokers, right? So with 9 times 0.45, so we're weighting this. And then here among non-smokers, the incidence was 1 per 1,000, but the proportion of non-smokers was 55%. So we add these two together because you either can be a smoker or a non-smoker, and we get 4.6 per 1,000. Okay. I note here that because it's an either or scenario, we can basically use the additional rule of probability. The additional rule is for either or scenarios. All right, let's calculate the population attributable risk. We take the incidence in the population, which we calculated to be 4.6, and we subtract the incidence among non-smokers. This is the background risk, so we get 3.6 per 1,000. The proportion of risk in the entire population that we can attribute to smoking, we do the same. We take the population attributable risk and divide it by the incidence in the total population, right? And we get 3.6, like we do here, per 1,000, and we get 4.6 per 1,000 as the incidence in the total population, and that rounds to 78.3%. So our interpretation. We can reduce the risk of CHD in the entire population by 3.6 per 1,000 individuals by helping people quit smoking. And we can reduce the risk of CHD in the entire population by 78% if we get smokers to quit smoking. A couple of practice problems for you all to work out. The following are data from the 2017-2018 National Health Interview Survey of workers in the United States who used e-cigarettes, they vaped, some days or every day at the time of the survey. We're interested in knowing if education level is related to vaping. So in this case, education level is our risk factor. Interesting, huh? You can use all kinds of risk factors. Like usually people who have lower levels of education are more likely to engage in certain behaviors. So that would be our risk factors. So we need to calculate the relative risk for current vaping based on education status, comparing those with a high school education or less, that's the risk factor, to those with greater than a high school education. In public health, we generally look at high school education or less versus greater than a high school education. We're going to calculate the attributable risk to having a high school education or less, calculate the proportion attributable risk, calculate the population attributable risk. So here's some, so I was having fun. So I went back, this was, I can't remember what year, this was maybe 2021 when I did this. I looked for values. So I tried to create, this is a problem that I created on my own. Note that the population estimate for completing a high school education or less based on National Center for Education Statistics data in 2016, so this in 2016 data was 39.7. So 39.7 individuals had a high school education or less in 2016. And here's some of our data. We have those who are exposed, those who have a high school education or less. This is how many vape, these who have greater than a high school education. And here's our totals. All right, so let's go ahead and take a look at this. Where did I have, here it is. All right. I was having some fun with this stuff. And my wonderful handwriting. First, I did the relative risk. So this is the risk among individuals who had a high school education or less. So we had 45,928. And of those, 2,185 vaped. And then among those who had greater than a high school education, we had 3,127 vaping. So our relative risk, so our risk of vaping was 67 times higher among those who had a high school education or less versus those who had a greater than high school education. Okay. Interesting, just in itself. If I were only doing relative risk, I'd provide a confidence interval for that too. But here our focus isn't on relative risk. Our focus is on the attributable risk. Okay, so let's look at the attributable risk. We need the risk among those who have less than a high school education. And from that, we're going to subtract the baseline risk, right? That's among those who have, that's risk among those who have greater than a high school education, right? So we had 2,185 or 45,928. And so basically we have these same values, this minus this, right? So we get a total of 0.0 0.0191. If we multiply that by 1,000, 1, 2, 3, move our decimal point 3 places to the right, we get an attributable risk of 19.1 per 1,000. If we take that attributable risk and divide it by the risk among those who are exposed to the risk factor, we get 0.401, or 40% of the risk is attributed to having a high school education or less. Okay. So basically, we can decrease the risk of vaping by 40% if we got people to complete high school. I mean, go further, go beyond high school. That's what that's saying. Or we can decrease the risk by 19.1 per 1,000 if people were to go beyond high school. Now, to do the population attributable risk, we need the proportion of individuals who had a high school education or less, and we saw that in the setup for this problem was 0.397 or 39.7% of the population in 2016. That was our estimate. And often we have to deal with estimates because that's all we have. I mean, hopefully it's higher, lower than that now. You know, I have no idea. I'd have to look that up. And then the complement of that is 1 minus the probability of having a high school education or less. 1 minus 0.397 is 0.603. All right, so we use these weights to reformulate our incidence, so it'll be population incidence. So we take our risk among those with less than or equal to a high school, multiplied by the proportion who have less than or equal to a high school education. To that, we'd add the risk among those who have greater than a high school education times the proportion of individuals who have greater than a high school education. And when we add those together, we get the population attributable risk to be 0.0361. If we were to multiply that by, well, actually, yeah, so that's our population, excuse me, that's our population attributable risk. Our population risk, excuse me, our population risk. To calculate our population attributable risk, I have to subtract the incidence among those who have greater than a high school education. So that's what we do here. So our new risk, our population attributable risk, is the difference between these two, which is 0.0076. Multiply that by 1,000, 1, 2, 3. Again, it's 3 zeros, 3 decimal places to the right. 1, 2, 3, we get 7.6 per 1,000. So what do we have here? We want to know what proportion of the risk is attributable to education. The proportion of this population risk is attributable to education. Well, we take the population attributable risk divided by the risk in the population, and we get 0.2105 or 21%. So our interpretation is attaining an education above high school only, whether an associate degree or something else, would result in a 21% decrease in the risk of vaping, or about 7.6 individuals per 1,000. It's pretty cool stuff, right? You got to have all these different tools in your toolbox when you're in public health and you're dealing with the population. In my courses, when I first started, I taught a lot about years of potential life loss. So years of potential life loss, that has to do with people dying prematurely. And when you die prematurely, you lose potential to do great things, right? Or do anything. So if our life expectancy is 85 years and somebody dies at 84 years, they've lost 1 year of potential life. If somebody dies as an infant, 1 year old, they've lost 84 years of potential life. So obviously, if somebody dies younger, that's more of a burden to society than if somebody dies earlier. DALYs adjusts year for potential life loss, which we'll just use YLL here, take out the potential, it's called years of life lost. It adjusts for the years that one lives with disability. So when one becomes ill, one may also experience disabilities, and those disabilities place a burden on their lives. Okay, so Essentially, DALYs, disability adjusted life years, accounts for the quality of life lost when one has to live with a disability. So YLD's years lived with disability, whether it's depression, COVID, anorexia, or anything. So let's talk a little bit about disability before we move forward. What is disability? Disability is defined by impairment, activity limitations, and participation restrictions. Impairment could be, well, is a loss of some function, could be something like a loss of vision, a loss of memory, a loss of a limb, or paralysis. An activity limitation is the inability to perform some actions, basic actions, and they're related to this, of course, to the impairment, like walking if one loses a leg, right? Typing, depending on what loss they have to their hands, fingers, arms, talking, seeing. So those are all activity limitations. And then participation restrictions are restrictions to activities one can engage in, right? Participate in, right? So for instance, it's the involvement in life situations that one loses when one has a disability. For instance, the ability to work, ability to play, ability to engage in interpersonal relationships. So here's an example. I like to push the limits. I remember in statistics, one of the interesting ways of testing an equation or doing a proof is to test the equation in a very extreme situation. So, well, let's test this definition in relation to mental illness rather than losing an arm or losing a leg. So let's focus on social phobia. So what is the impairment in social phobia? These are all my hypotheses here. I mean, some clinical psychologists can correct me if I'm wrong, but it's the inability to self-regulate emotion. Emotion kind of takes over. Activity limitation, like speaking, for instance, like especially in front of crowds, eye contact, these are issues that would be a problem. Participation restriction, interpersonal relationships, jobs. I mean, if job involves public speaking or greeting people, it'd be very difficult for somebody with social phobia. Interpersonal relationships would be hard if one can't make eye contact. So how do we calculate DALYs? Well, DALY includes both years living with a disability. It's the sum of the years living with a disability plus the years of life lost. So we're just adding the years living with a disability to the YLLs. To calculate the YLL, we take the death at an age, and generally we don't do every age, because if somebody dies at 71 years, we'd have to start at birth and work our way to 71. We'd be doing 72 different calculations. So we don't do that. Generally, we work in different strata, like strata could be 5 years, these 5 years chunk of age. So we'd have deaths at that age stratum times life expectancy minus age of death. So what we do then is we are able to calculate how many people, the product of how many people died in a specific stratum times the years of life lost. So that's how we get our YLLs. For the years of living with disability, we need the number of cases. So how many people we're looking at, the duration until remission or death, because somebody can actually be cured, or of course they die. And then we need this thing called a disability weight. This is the only one where we can't just calculate on our own. I mean, we can estimate it, but generally we rely on a bunch of experts to get together and come up with a disability weight. So it's a condition-specific weight. So you're given a disability. Disability weights, they reflect the proportion of life lived with a disability. So a disability weight of 0 means there's perfect health, because think about it. You multiply this times 0, you get 0. If the disability weight is 1, that means complete absence of health. That's the worst possible scenario. Okay. So here's an example. A disability of weight of 0.3 means that one lost 30% of each year of life with the condition to the disability, or that one has lived 70% of each year of life with the condition without disability. So I mean, you're still kind of in the plus, and if your disability weight is 0.3 because you live 70% of your life while having that condition without the disability. So it's still not horrible if your disability weight is 0.3. Here's an example. Suppose 5 individuals contracted COVID-19 and continued to experience symptoms for 5 years after infection. These individuals died early. So let's say the age stratum is 60 to 64. That's a 5-year period. So they died at that time point, and the midpoint for that 5-year period is 62.5. The way I got that is by taking 60 and adding 64 to it, and then adding 1 and dividing that by 2. Why we add 1 is because we start at 0. Right? We don't start at 1, right? We always start first year is 0, right? 0 to 1 is 1 year. So if life expectancy for these individuals is 85 years, what is the DALY? So I'm going to use the disability weight of 0.219. This is based on this Cushieri and Calleja article in 2021 that gave like a disability of weight for COVID. So we needed somebody to give us that weight. It was based on some kind of a panel agreement. So for the years of potential life loss, or YLLs, we have 5 individuals, right? They died in this period 60 to 64. The midpoint of that age range was 62.5. Our life expectancy is 85, so it's 5 times 85 minus 62.5. So we had 112.5 years of potential life loss because those 5 people died. Again, it's counting for everybody, every one of those 5 people, not just one person. For years living with disability, well, these 5 individuals live 5 years. There's 5 times 5, that's 25, times the disability weight, we get 5.475. So our DALYs is 5.475 plus 112.5, so we get 117.975. So how would we interpret it? How would we interpret this? These individuals lost basically 118 years of healthy and potential life due to COVID-19. Not just their death, but also their life living with the disability. So this is a better measure than just the YLL, which is 112.5. So we're accounting for the fact that people have to live with a disability. And if you want more information for the burden of deaths and disability, you can click this link here. So you'll find it for specific countries, etc., and diseases. All right, let's talk a little bit about causation. People make all kinds of claims. I'm going to talk about COVID because that's where we're still, even though COVID seems to be in a rear view mirror to some, it's still around, and people still make up stuff about, I was going to say a dirty word there. They make up stuff about COVID. All right. Like, for instance, we hear people who say masks don't work, or vaccinations don't work, or vaccines kill people. I've heard people say that so many times. Vaccines cause infertility. There's so much misinformation out there. We don't know what's true and what's not true. But as a good scientist, you have to investigate everything. So we need to better understand how we should judge causation. So I'll give you some guidelines that you should use. Everybody should use this. First, temporal precedence is important. A cause must precede an effect. So if one has COVID and then starts wearing masks, masks can't be the reason why somebody got COVID or not wearing a mask. It would have to be wearing a mask would have to precede COVID for one to say that wearing a mask does or does not affect COVID or new case of COVID. Strength of association, the stronger the association or stronger associations indicate possible causation. We often say that correlation is not the same as causation, and that is absolutely true. But correlation is sort of a prerequisite. I mean, they should be related, right? If they're not related, how can they be causally related? If they're not related just by association. Dose-response relation, a higher dose, greater effect. So, for example, exercise causes happiness. The evidence of a dose-response relation would be more one exercise, the happier one is. Alcohol and being drunk, the more one drinks, the more drunk one is. I mean, that's like a dose-response relation. Replication of finding. Science requires replications. even though replications don't seem to be fun or they don't seem to get all the publicity, we need replication. If we find something one time and never again, it's nothing but an accidental finding. I mean, if you know anything about statistics and the sampling distribution of things like the mean or whatever test statistic we're working, whatever parameter we're working with, the sampling distribution, well, you're going to have samples falling at different parts of our distribution. Some are going to be above, some are going to be below the mean. We need a lot of samples from the population in order to make a solid conclusion. And they all have to basically replicate each other, right? It can't just be, one finding only. That one finding, again, is just probably an accidental finding. People do get very excited about these unique findings. You should always look at them with caution. Biological plausibility, demonstrating a plausible biologic pathway. Well, if we look at an example of exercise and happiness, it's plausible because exercise increases the release of dopamine, which is rewarding. So, I mean, I can see a person being happier because they're having, a higher experience of dopamine, this reward molecule. Consideration of alternative explanations. You always have to look at alternative explanations, and people don't like that. Like, you have to rule out competing explanations, especially if we're working with what are called cross-sectional data, right? Data that are taken at one time point where we don't have temporal precedence. So, for instance, if one claims that masks don't work to prevent a virus, transmission of a virus, they must rule out with evidence the possibility that masks do work to reduce the transmission. Most people who are anti-maskers, they never provide evidence that, to the contrary. They just say they don't work, and they expect you to believe it. In cases we've been hearing lately, people use loud voices to replace good evidence. Cessation of exposure, the exposure ceases, the effect is removed. You can think about that either with exercise. We would have to show that removing exercise decreases happiness. Well, think of it in terms of allergies. If you put a cat in front of a person who is allergic to cat dander, and the person starts sneezing, you remove the cat, and the person sneezes no longer. Well, there you go. You got cessation of exposure. Consistency with other knowledge. Well, this shouldn't be just a one-off. There should be other knowledge that is consistent with what you found. An example that I provide is distracted driving. So distracted driving is related to automobile accidents. I mean, every day I see people looking at their phones while they're driving. They start swaying across, side to side on the road. Of course, I'm looking at them, looking at their phones, so now I'm being distracted. Well, that's a plausible explanation, right? Distracted driving causes accidents. It's plausible because we understand the limitations of working memory. Working memory isn't infinite. It's limited to the amount of information we can process at one time. Like a phone number. When we used to remember phone numbers, that's about 7 bits of information. We are limited in what we can process. So yes, that's plausible that distracted driving can cause accidents. Specific association, the risk factors associated with one and only one disease. That's a tough one because a lot of the risk factors we look at have many potential outcomes. Some claim that suicide among football players is caused by concussions, but that's a problem because concussions also cause CTE and have other effects like mild cognitive impairments. So it'd have to have one and only one outcome. So let's look at the steps for conducting an experiment, since we're talking about experiments. Experimental designs with randomization and control groups are the only type of study that permits determining causation because we have such perfect control and we randomly assign people to the different groups, and we need some kind of a control, some kind of thing like a placebo, a sugar pill if we're doing a drug study. So here are the steps that we would do. We'd write out a research question. We'd operationalize our independent variable and our dependent variable being the variable of interest, and our independent variable being the variable we're manipulating. Like, for instance, assignment to an experimental group versus a control group, to a drug versus a placebo. Operationalizing variables means just defining them so we can operate on them. Like, what exactly is self-esteem? Well, it's whatever is measured by the Rosenberg self-esteem scale. Well, that's easy. Write out our hypotheses. Our null hypothesis is the hypothesis we generally like to reject. Like in this case, I use Greek letters to indicate population mean. So population mean for this group is equal to the population mean for this group. So the one we'd like to reject. So if I'm, like, say I'm comparing a placebo to a drug, if they don't work, the effect on, say, happiness would be the same for the drug or the placebo. So that's why we'd have the equal. Then we write some sort of an alternative hypothesis, either that the two groups are not equal or one group exceeds the other group, either one direction or the other direction. This should be actually H sub 1. Sorry about that. Sometimes I get too, yeah, I forget. One, there you go. And here, delete one. Okay. So H1, or some people write HA for the alternative hypothesis. Select our research design. We'd like the randomized controlled trial. If we use a non-RCT, well, we're going to have some issues, in terms of claiming causation. Non-random assignment, we introduce all kinds of problems like selection bias, and sometimes we compare groups, like, because they just exist, two different classrooms. One has a certain type of teaching method and the other doesn't, and there's a lot of factors that can compete with our predictor variable, our independent variable. Assuming randomized control trial, I would say the best way to test the efficacy of our treatment would be some kind of a between within design, where we look at change. Within means change over time, like from pre-treatment to post-treatment, right? Pre to post, and then between, say we have a drug versus the placebo, and we try to figure this out. We look at the interaction between time and the assignment to the drug group. Select our ideal participant based on exclusion and exclusion criteria. So we identify the number of participants required, the sample size. That's something that's done by statisticians generally. Generate a participant recruitment strategy. How are we going to recruit our participants? Usually we have to figure that out because that's time consuming. We need to hire the amount of people. How much we're going to pay them if we do pay them. Usually people want to get paid for participation. Prepare our institutional review board application. That's our IRB. That's to help determine whether or not we're committing any kind of ethical violations. Prepare our data collection strategy, like how are we going to collect our data? Identify the best strategy for randomization to the different levels of the independent variable. So if we're doing a randomized control study, we have to randomly assign individuals to different groups. I have lectures on this, I believe. Recently, I've posted some, so you can take a look at those in my my page, my YouTube page. By the way, you should subscribe to my YouTube channel because I have a lot of awesome videos that can help you become a better student and meet your education academic goals. And plus, I also have a lot of good skiing videos if you like skiing. Recruitment, who is your ideal participant? So there are comorbid conditions you want to rule out. Like if I don't know if I'm doing obesity or depression. I'm sorry, not if I'm doing obesity, I might want to rule out type 2 diabetes or something like that. Those are generally comorbid conditions that occur together with other conditions. That's what comorbid means. What is your plan to recruit participants? Will participants be offered, like I said, incentives to participate in a study? The IRB, all studies must receive IRB approval. Some studies can be exempt from IRBs, having to take an IRB meeting or getting IRB approval, but they have to meet very, very strict definitions. I mean, for instance, you can't have like anything that would allow the participant to be identified, not even sex, race, anything at all. So what we're doing with the IRBs, we're just trying to make sure that the benefits to the population as a whole of the study outweigh the risk to the participants. Then we engage in data collection. We want to know how our data going to be collected. So one would state what procedures will participants undergo. Oh, this is still with the IRB, what they will undergo, and timeline would be helpful, like, you know, how long this study going to take to complete. So anyway, that's what we do in conducting studies. Once we get all the data, of course, we do our data analysis and do our statistical. We enter our data and then do our statistical analyses, find a result, write papers, go to conferences, present our findings at conferences, present them in publications, hopefully, and then apply for more research grants to follow up these studies. So if conducting research is just an ongoing process. The idea, again, is to replicate findings, because we know that the more results we get that are similar with different participants, the better off are we, the more able are we to hint at causal associations. That, my friends, is this lecture. I hope you enjoyed it. If you have any questions, please ask, and please, please, please like and subscribe to this video. Thank you very much.